Hi everyone, it's Miss Park here. I hope everyone's doing well. So yesterday Miss Polham covered the concept of equilibrium, and today I'm going to cover something that is related to equilibrium called equilibrium constant. So this is today's lesson goal and success criteria. So just a quick recap on equilibrium. So equilibrium is represented by this double-headed arrow. So the top arrow is representing reactants forming products, and the bottom one is representing products forming reactants. And there are three things that you should have in mind when you're thinking about equilibrium. So at equilibrium, the rate of forward and the rate of reverse reactions is the same. So that means that the frequency of successful collisions of reactants going to products is the same as the frequency of successful collisions of products forming reactants. And we can see that in the ants animation. The speed at which this ant is moving from reactants to products is the same as the speed at which this ant is moving from products to reactants. And second point is that the concentrations of the reactants and products don't change. So even though this ant is moving one rock from products to reactants, because this ant is also moving one rock from reactants to products, the overall concentrations of the reactants and the concentrations of products, they don't change. And in some reactions, at equilibrium, the concentration of reactants might be greater than the concentration of products. Or the reactant concentration might be less than the product concentration. But in other cases, the concentration of reactants might be the same as the product concentration. And in this example, we have a higher concentration of reactants than the products. So how can we find out about the relative concentrations in a reaction? And that's what we're going to cover today. We're going to learn about equilibrium constant. So an equilibrium constant is a number that represents the ratio of the concentration of products at equilibrium to the concentration of reactants at equilibrium. And you can use this figure, you can use equilibrium constant to figure out the relative quantities of products compared to reactants at equilibrium. I know it's very wordy, but it'll become much clearer once we start to look at the equilibrium constant expression. And just to mention, the symbol for equilibrium constant is Kc. So before we move on to equilibrium constant expression, we need to understand, what a chemical equation means. So here I have I got the lowercase letters in red, which represents the number of moles. And this black uppercase letters, they represent the atoms and molecules of the reaction. So let's look at this example. So we have 2 moles of nitric oxide and 1 mole of oxygen. And remember this equilibrium arrow. And then we have 2 moles of nitrogen dioxide. So that's what is included in a chemical equation. And it's important that we understand this to write the equilibrium constant expression. So here we have this is how you write the equilibrium constant expression. So this is just a general expression. So Kc, which is the equilibrium constant, equals the concentration of products, so C and D, over reactants, the concentration of the reactants, A and B. So that makes sense. Now, what about the moles, right? We can't forget about them. The moles, for each molecule or atom, they go at the top as an exponent. So I want you to see that I put a square bracket, not a round one like this, but a square bracket, because that represents concentration. So if C is in a square bracket, that means concentration of C. And concentration is in mole per liter. So as I said, products are always written above reactants. And one thing to note, which is very, very important, is that solids and liquids are not included in equilibrium expressions, equilibrium constant expressions. So you can add aqueous or gaseous states, but not solids or liquids. So let's go through an example. So here we have 2 moles of hydrogen gas and sulfur solid at equilibrium with 2 moles of H2S. Forgot how to say that. So it's always important to check the state. Yep, gas. Oh, solid. And there's gas. So let's go to the equilibrium constant expression. So as usual, you have to make sure you add Kc equals. But you can see that we only have, one product and one reactant. Where has S2 gone? Well, that's because we can't add sulfur because it's solid. It has no place in equilibrium constant expression. So we can include H2S and H2 because they are gas. They're not liquid or solid. So remember, products on top, which is why we have H2S at the top and H2 at the bottom. And don't forget to put the square brackets to say it's the concentration we're talking about. And remember, we have to put moles at the top right corner as the exponent. So that's why we have 2 at the top for H2S, because we have 2 moles of H2S. And again, 2 at the top for H2, because we have 2 moles of hydrogen gas. So you can pause this lesson to have a go at these questions. And here are the answers. Hope you guys did well. So we do have more practice questions on SciPad if you want to have a go at them. And well done if you got all of these right. But if you didn't, then make sure you check where you went wrong and correct your mistake. And I can already tell what I did wrong here. Make sure you put Kc equals, because if you don't have, Kc equals this, then that's not really a equilibrium constant expression, is it? Yep, so sorry guys. Okay, so what information can we get from Kc? Well, the equilibrium constant only gives information on how far the reaction proceeds. Has it gotten to completion? Or, is it close to being completed? Or is it just far off? And Kc gives no information on the rate of reaction. So just by looking at the value of Kc, we don't know how fast the reaction occurs, or the frequency of successful collisions. So as I said, we can use Kc to determine how far a reaction proceeds. So if the size of Kc is greater than 1 times 10 to the power of 20, which is the same as 1 with 20 zeros, so 1 0 0 0 0 0, I have no idea. That's very large. And that means that the reaction has gone to completion. All products have formed, and there are no reactants remaining in the reaction. Now, if Kc, the size of Kc is greater than 1, we consider that large. That means that the reaction is at equilibrium, but there is a higher concentration of products than reactants. But if Kc is, less than 1, we consider that small, and that means the reaction is at equilibrium, but there is a higher concentration of reactants than products. And if Kc is less than 1 times 10 to the power of negative 20, we consider that very, very small. Okay, very small. That means the reaction will not occur. It's not going to happen. And all the reactants will remain unreacted. So, for these two, the reaction has either gone into completion, or there is still more products. And when that happens, when that's the case, Kc, the value of Kc will be greater than 1. But for these two, the reaction is either has not even started, or is not going to occur, or there is higher concentration of reactants than products. And the Kc, the value of Kc will always be less than 1. And that makes sense, right? If you look at the equilibrium constant expression. Remember, product at top and reactants at the bottom. If you have higher concentration of products, so greater number on top and lower value at the bottom, top and bottom, then Kc will be greater than 1, right? If it's 2 here and 1 here, it's going to be 2. It's greater than 1. And that means, we have more products and less reactants. But if we have, more reactants, so greater value at the bottom and smaller value at top, that means we're going to get something, the Kc value is going to be less than 1. It'll be 0 point something. And if Kc equals to 1, what does that mean? So if it's 50 divided by 50, that means the concentration of products is equal to concentration of reactants. Let's do a quick recap on Standard's notation. So here we have 5.0 times 10 to the power of 5, which is equal to 500,000. That's very, very large. Now, if you pay attention to here, if there is nothing, no positive, if there is no negative value, that means it's positive. And that means that the value will always be greater than what you have here. So, 500,000 is greater than 5.0. And even if it's just 10 to the power of 1, so if it's 5.0 times 10 to the power of 1, that's still going to be 50, which is larger than 5.0. But if, let's say, 5.0 times 10 to the power of negative 5, so you have a negative sign in front of the exponent, then you're going to have a very small value, a value that is smaller than 5.0, like this, 0.00005, which is very small. So always pay attention to if there is a negative sign or nothing. So let's make a link to equilibrium constant. So if Kc is 5.0 times 10 to the power of 5, and that means the concentration of products is 500,000 times the concentration of reactants. And that's a lot. And that means, if we go back, that belongs around here. So reaction is at equilibrium, but there is a higher concentration of products than reactants. Let's look at this. If Kc is 5.0 times 10 to the power of negative 5, that means the concentration of products is 0.00005 times the concentration of reactants. And that's very small. So let's look back. Yep, so that belongs here, right? The reaction is at equilibrium, but there is a higher concentration of reactants than products. So as I said, we can use Kc, which shows how far the reaction proceeds. So let's look at this example. So I have no idea how to say these, but this cobalt water complex has a pink color, whereas this product cobalt chloride complex has a blue color. If Kc of this reaction was 4.0 times 10 to the power of negative 4, what would the color of the solution be? Well, we can always go back to this table. Well, we know because it's, to the power of minus, to the power of a negative, it's going to belong in these two bottom rows. It's not as small as, 10 to the power of negative 20, so it's going to belong here. And that means that the reaction is at equilibrium, but there is a higher concentration of reactants than products. Well, if there is higher concentration of reactants than products, then the color is going to be or closer to pink. But if Kc is equal to 2.6 times 10 to the power of 9, what would the color of the solution be? Well, let's go back to the table. It's going to belong here. Because it's not as large as 10 to the power of 20, but it's in between 1 and 10 to the power of 20. So the reaction is at equilibrium, but there is a higher concentration of products than reactants. So because we have more products than reactants, the color of the solution will be closer to blue because we have more of this. So here it is. Yep, so pink for this Kc and blue for this Kc value. We have another example. So here we have 2 moles of nitrogen dioxide, which is dark brown, at equilibrium with dinitrogen tetroxide, which is colorless. So at 0 second, there were 100 NO2 particles and 0 N2O4 particles, which is why the color of the reaction is dark brown. But at 10 seconds, 10 of NO2 particles reacted to form 5 N2O4 particles. And that makes sense because here we have, you need 2 NO2s to form 1 N2O4. That's why we needed 10 NO2s to form 5 N2O4s. And because, we still have a greater number of NO2 particles, it's going to be dark brown. But at equilibrium, at 30 seconds, we have 60 NO2 particles compared to 20 N2O4 particles. Yes, it's going to be, still brown, but it'll be less dark brown than it was at 0 and 10 seconds. So yeah, so the reaction will be brown at equilibrium because there are more brown NO2 particles and colorless N2O4 particles. And when the reaction is finished and there is only N2O4 particles, then the reaction will be colorless. Now at equilibrium, because we have more reactants than products, Kc is going to be small, less than 1. So I have a question for you to work on. A chemist wants to find a cost-effective way, which just means she wants to cover most of the reactant to product to produce NO. Now she had several unsuccessful trials, and this time she decided to use a reaction using NaCl. Looking at the Kc value, do you think she'll be successful this time? So here is the chemical reaction, and here is the Kc value. Use these two information to answer this question. Okay, thank you guys.